the talk will be 45 minutes, and afterwards you can queue up at the mics here and here. So in the center and to the left of the stage. We don't have an audio angel to the right, so yeah, the left and the middle. Thank you. Bex.
Thank you. I would like to thank you all for waking up so damn early to come to my talk, but I really appreciate it. So I come from Dartmouth College, and that's over in New Hampshire, that teeny little state up in red on the map in the US. It snows, and sometimes we build ships out of snow, and if it's too cold to be outside to build the ship, we bring one inside our lab and do shippy things. So this talk in 1 minute, I just want to introduce Sergey Bradis's Weird Machine Zoo, in case you haven't heard it before, because this is part of his collection. And the specimen we'll be looking at specifically is the ELF linker loader. We also look at other formats just to see where we can get with weird machines. And so I'll start with some background just to get everyone up to speed of what mechanisms we're using. And we'll be programming with ELF metadata, not code. There'll be no machine code involved other than whatever happens to be executing the metadata. We're crafting metadata only, and there'll be no changes to code in either the libraries, the linker, the executable itself. And then I'll show just a proof of concept ping backdoor, what you can do with just metadata. Go a bit into Mako, which is some initial work, and some notes on PE. So what is a weird machine? So they've always existed, but there's never necessarily a name to weird machine, but it's just undocumented, unexpected sources of computation in some target, in an executable, or in maybe embedded hardware or whatnot. All over the place. Weird machines are everywhere. And they can be triggered by weird or crafted data, or sometimes they're just triggered by code, but I'm focusing on data. And so they're often used in exploits. And so where do we see this? Well, return-oriented programming is a weird machine. You craft up a stack, and suddenly you're executing something that normally isn't there, something that you don't expect necessarily, but just because the way things are laid out in memory and the way you can access any piece of code, you get this weird, you can end up crafting some weird computation. In heaps, when you try in heap crafting attacks, anything that involves trying to get the heap into a predictable state, that's a weird machine right there, trying to make a lot of mallocs and frees so that the so-called randomized heap ends up being more predictable, and then the attack can continue, perhaps overriding some function address. And then what we're looking at is the linker loader metadata and weird machines that we end up finding just by how the metadata is processed. And so many forms of weird machines. So there's the toilet-like forms, like SQL injection, or we can have the combo toilet washing machines, the little more cool stuff like ROP, and then the really, really weird stuff like crafting ELF. And I also think heap smashing is kind of odd and dwarf. But these are just kind of ways to think about weird machines and examples of them, because you never really expect, or these types of computation, these types of attacks weren't really intended to exist, but they do. And so focusing on data as an attack vector, this is a famous image in our lab. We use it a lot, and it's called composition kills. So how do we influence execution? We want to data can influence via side effects, and so side effects, if they're interesting side effects, will end up changing the way execution happens, the code path that ends up being taken, dependent on the data itself and how operations are happening on it. And so a simple example may be just changing the entry point in perhaps ELF. And so some other code is jumped to first instead of what normally is. Or format string attacks are pretty weird crafted data that ends up being an attack vector, or can be one. Or overwriting, so a lot of examples are in just overwriting addresses that end up being called as functions. And now metadata describing the execution environment end up being this attack vector. So why metadata? A lot of previous work in executable metadata crafting all involves trying to get some injected code to run. So you might patch up the way the libraries are loaded, or you might patch up some entry points. But that tends to be the goal. And so a lot of focus on antivirus and such. I'm not going to say too much about antivirus or say whether or not I like it, but there's a focus on code. And I want to show that code is not the only place to focus. There is so many other things that influence execution. And maybe I'm thinking it's challenging to defend against. How do you distinguish good from evil, well-formed data? And then distinguish the expected from the unexpected, the intended from the unintended. And the defense would be to reduce computational power, but how do you do that without breaking what needs to be done? So it just takes a lot more engineering and thought. So I think to defend against these metadata crafting attacks that cause weird machines or that control weird machines, program weird machines. And then, so this resulting control flow is sort of indirectly dependent on data. So trying to understand it takes a couple layers of indirection. And in a sense, it's kind of obfuscated because you don't just see the code that causes the weird behavior. You're looking at metadata, and you have to understand how the metadata is operated upon. And then another fun thing is, after giving similar versions of this talk, I have heard certain vendors say, oh crap, we don't sign our metadata, we only sign our code. So it's good to know what else can be done. So you can really ensure that whatever executable or whatever you want to sign you don't have unintended differences because you signed the wrong things. So here's our case study of some specimen in the weird machine zoo using ELF metadata as instructions. And I'll start with a small crash course in ELF, focusing on just what we need. So what is it? It's how the compiler components communicate. It's what I like to say. These different ELF files are, say, if it's an executable, it's the linker's love note to the loader. It's all the data that needs to be known to be up so the next component in the tool chain can properly do its thing. So just to think about this tool chain I'm talking about, we start with source code. We invoke GCC and get an ELF object, which is a relocatable file. And then you run the static linker among different object files, perhaps, and end up with an executable, or you can end up with a library. And then the part that I'm focusing on is when this executable is being loaded and other libraries are being loaded before it's run, before the entry point of this executable is jumped into. And so there's a lot of different components to ELF files, and I don't want to waste your time. I will only look at symbols, relocation entries, and dynamic linking, because those are the three things that we work with, the three types of metadata. So symbol tables. Symbol tables provide information to allow you to locate or relocate symbolic definitions and references. So you'll see it for functions that are imported to an executable, something used from a library, or the library itself will have symbols for anything it's exporting. So an example in libc is these are some values that are actually what compose the symbol. And so standard in has an entry, and they specify it's a type object. They give a size, meaning it depends how size is, what this is and how size is interpreted, but there's different meanings depending on a lot of context and how the symbol is processed. But then maybe, standard, and I said it's function, it's not function. It's just a value, but put C as a function, and so it's represented a little differently in the symbol table. And this is for AMD 64. This is how these references, these structures look. There's usually there's a pointer to a name. Sometimes the name is just empty. There's some, meta info about this, whatever this symbol is or what it's representing. Some value usually used during relocation, and a size, and so forth. So just lots of little metadata to help with this linking and loading process. And so for relocation, there's metadata used to describe how things should be patched during loading or during linking. So for AMD64, we get an offset. So where should we write the address to? Info, which tells what type of relocation entry it is. And that will actually, the way the addresses are patched will be dependent on both the type of the relocation entry and the symbol if the relocation entry refers to a symbol. And an indent, which extra values can be added in. So the dynamic table is a metadata that's used pretty exclusively by the runtime linker and loader. It's this one-stop shop to know where everything is, everything that it needs to know about the executable or the library. And it's really just a table with types and value pairs. And values often point into other tables. So ones that are interesting are this rela and rela size, which just points to the table of relocation entries and specifies the size. And then we have one that points to the location of the symbol table, so that it knows where the symbol table is. And these things, including the rest of the ELF file, are in entirety loaded into memory at runtime, so that it's available later on, and so that it can be used later on. So the GOT and PLT are essential for our lazy linking, for linking in a function during runtime. So there's an entry for each function that needs to be linked in both the GOT and the PLT. The first, two of the slots of the GOT have some special data. So one points to the link map structure, which is this type of structure. This structure is where the loader and linker keep all the information it needs of the environment. And then the second one is just entry points into the dynamic linker, so that when a symbol needs to be dynamically linked, it knows where the code is that actually does the linking. And then the PLT, and so the other GOT entries have, it's either an address to the function itself if it's been patched, or the address to the top of the PLT. And the PLT works with the GOT to end up either invoking the LF fixup or the library function. And if the top of the PLT contains the instructions and end up invoking DL fixup. Otherwise, the GOT entry will work with some specific entry in the PLT table just for that function. So this is sort of a crash course in the memory layout. So everything got loaded. At this point, we're assuming all the libraries are loaded too. So at the top, typically, if there's no randomization of the executable itself, which I rarely see the executable being randomized, it's always mapped to the same spot. And the red I have is read execute. Yellow means read only, and green means read write. So typically, well, always, the executable code is mapped into read-only. And so everything for executable in the text section, which is where the code is mapped. And then after it, you'll find read-only data that the executable might need, and also read-only data from the ELF metadata mapped into that portion. And so relocation entries and symbol table entries are typically mapped there. And then we have information mapped from the dynamic table mapped into write space. And you see similar segments for all the libraries. You'll have a text segment, you'll have a data segment, and then you'll have another data segment that's read-write. And an interesting library is the loader itself. That is also mapped in. And one thing I want to really focus on is within this, there's a read-write table that actually has data on all the libraries that are loaded. And this link map structure is what keeps track of data needed for each library. So you'll see the base address for the library, you'll see pointers into the dynamic table, and you'll see they have, it's a doubly linked list, so they point to their neighboring link map structures. And the order in which these are located or pointing to each other is actually the order in which symbol lookups are done. So this kind of ends the general part of ELF. I just want to warn you that the weird machine I found is kind of specific to the AMD64 architecture and Ubuntu glibc 213, that GCC tool chain right there. And I believe that would work in others, but this is where I worked. And so if anyone wants to try this at home and they have a different tool chain and architecture, and I'd be really interested to see what type of patches need to be done to get it to work in other places. So these are the relocation entries that are used for AMD64. Okay, there's a lot more than this, but these are the 3 that are used for the metadata weird machine. So there's a copy, which really just acts like memcopy, and the symbol that it points to is where you're copying from and the number of bytes, and the offset is where you're copying to. And so the 64 type, it's a very standard relocation entry. If there's a base, so base means wherever the object, the whole library or executable is loaded. And that will add it to the offset. And from there, we'll write the value of the symbol plus the addend that's specified in the relocation entry, plus if the base, if, again, it's not loaded at 0. And the relative type of entry is actually doesn't work with a symbol. It just, you specify an offset and you specify a value to write into the offset. And if it's not loaded at 0, it will add some base. But because we're working in this particular talk with just executables, base is always 0. Most executables are loaded there. You have to compile it with certain flags to get the executable to be loaded at places other than 0/randomly, just to reiterate. So these are really cool types of symbols, these indirect functions. And it's relatively new in the GCC toolchain. And these type of symbols, the value is treated as a function pointer, and the function is called, and whatever it returns is what is written into the offset specified, the relocation entry. So we get ourselves, we can get ourselves arbitrary computation from this type of indirect function, and allows decisions to be made at runtime what function to patch, or what address to patch, or value to patch into the address. And this is where we start building into our language. So the Yelp metadata language call has 3 basic instructions, and I just want to do basic things so we can start building something a little more powerful. We can add, we can move our copy value. So if you're familiar with assembly, we also have sort of a load effective address that move can cover, and jump if not 0. So we can start getting branches, and this is just from metadata. We don't add any code, we don't change any code in the executable, only metadata. So symbol table entries act as variables coupled with metadata. And if you're familiar with assembly, I kind of like to think of them with registers that are memory mapped with metadata. And the relocation entries act as instructions. And they need to be able to, if you want the full power of the weird machine, you need to be able to read and write other instructions, other relocation entries. You need to be able to read and write other variables or symbols. And you need to be able to read or write, which is by default, the loader's data, the link map data that I showed earlier. And so the language, if we start thinking about this in just at a high level, we have operands, a destination, and instruction. And so all destinations are specified directly, so store the address, store the result at this address right here. And then for operands, depending on the instruction, there's different ways to address these values, these variables I've been calling them. You can either specify the operand directly, so right in the relocation entry, right in the instruction, you just say, this is the value. Or that value could be a pointer, so I'm calling that direct. If the relocation entry works with a symbol, I'm calling that a variable. So inside the relocation, there will be an index into the symbol table. And from there, you'll look at the value of the symbol, and that gets written. Or I'm calling variable indirect. So the symbol that the relocation entry works with has an address. And from that address, you read the value out. So this is how we implement move with relocation entry. And this is one of the simpler ones. It doesn't use symbols, so we're going to look at this first. And just to the left, I just listed addresses in memory, and I made these up. But just so we can start looking at something a little more concrete. The green at the top is just what the relocation entries look like that implement this instruction. And the gray is just more regions of memory that we're operating on. So in this example, we're going to look at moving a direct value 4 to, moving an immediate value 4 to something that's direct, so we specify the address. And this is done with a relocation of entry of type relative. So it doesn't actually use a symbol. You specify the offset, so where to make the move. And then the addend is specified directly into the relocation entry. And finally, at the end, it's copied. And with proper endianness, I just put that as a note. It's just easier to read this way. But this, the endianness does take is actually followed during these copies and moves, and they're treated as 64-bit values by default. There's some that work with 32 bits, but we won't look at those. So the move instruction, to do sort of an indirect move, sort of a load effective address, the destination is directly specified, and the value is indirectly specified. So the variable, the variable, which is the symbol, its value is an address, and from there you look up what to move. So this sort of indirect move, and our example is we're moving whatever from foo. I'm just naming a symbol, but really it's going to, in reality, it's an index into the symbol table. But let's work with names. And so those are sort of the other fields. The value here is beef. The shindex we're going to ignore. It's not looked at. And then size 8, which is used. So this time we use relocation entry of type copy. And that just does a mem copy. So look up the symbol, find the offset and where to copy, find the address and where we're copying from, and then the size, how many bytes to copy, and the copy gets done. So that is how our move indirect is implemented. So just a single copy instruction. So for addition, the destination, again, is directly specified as a value. Then the first operand is a symbol, is a variable, and the symbol has the value of the symbol is the one that's copied. And the second operand is immediately specified, so the value is directly specified in the instruction. And so this uses a relocation entry of type 64, and I'm not writing out the full relocation entry types, but it's of type 64, and that just kind of means the number of bits from the symbol. And so we look up the values that we end up writing. So it's the addend plus the value of the symbol itself, and finally add into the correct location. So jump if not 0 is quite an interesting instruction. In both value, the destination and the value to test are directly specified in a sense. It's not that easy though. It's not a single relocation entry that will be able to do jump for us. It's not designed for that. The loader doesn't just not process the next relocation entry. It's not part of the spec. So what do? We have to figure out, first of all, how to get the relocation, to get the loader to stop processing relocation entries. And this is a trimmed down version of the code that ends up doing the relocation. And this loops over every single link map structure in that doubly linked list that we have. As we can see, it just follows the pointer. And so in order to get it to want to process our own relocation entries again, because in the idea is, well, because we're doing a direct jump to somewhere else in our program, and it's all in the same executable relocation table, we want to set a loop into the structure. So that's one thing that needs to be done. So that would probably take a relocation entry. The next thing is it actually does some sanity checking to make sure it doesn't relocate the same table twice. So we need to somehow unset that bit, right? Well, it's actually a bit. We need to unset that. And then if you don't set this to 0, you have some issues. Later on, the relocation entries will end up being marked as read-only, and we don't want that. And so to fix the L relocated thing, we take advantage of other computation that happens in this loop. So there's something that follows a pointer and sets the value as 1. So if we can have it write this, 4 bytes of 1, I forget actually how big it is, and have it overwrite that 1 bit that gets tested to see if we were relocated before, then we can write a 0 into L relocated and trick the next step into relocating everything again. And at the end, you want to kind of fix all the data you messed up by writing a 1 into the correct place so that we zero out relocated. But I'm going to not go into detail about that because you have to really inspect it deeply. So to prepare to do for a branch, we have these are 4 instructions that do this patch we need. So L relocated becomes 0. The next instruction, this move, is how we build this loop into the link map structure to process ourselves again. And so you kind of get the idea that you're moving values and patching up the dynamic loader's runtime so that you can trick it into doing what you want. And then remember the table that specifies where the relocation entries are and the size of the table, you need to patch that. And it will, these values will be read again the next time it processes the entries. So if you just set the DT-rela to the address of what you want to process next, it will start processing relocation entries from there. And then you want to set size so it doesn't process too many. So to do an unconditional branch, we need to look at how a single table is processed. And it's a very simple loop. It just processes 1 relocation entry and then finds the next one, and they're all in the big table in memory. So it just hops around. And so this value of end is stored in a stack. But that's what we want to change. We want to set it so it's smaller than the address of the next relocation entry to force this branch. And it turns out that we can get the address of this stack at the runtime using relocation entries. There is a value in the loader that points to something on the stack. So all you need to do is find where the loader is mapped to memory, which I'll show you how, and then add the offset, and suddenly you'll find an address of something that's on the stack and work from there. And at that point, everything is very, when you're doing the loading, the stack will always be the same every time as long as you can find the base. So again, to continue, we're going to put these together to do the conditional branching. So the bookkeeping that was discussed, we need to do. And now we need something else that actually can do this conditional branch. So the ifunc symbol, the indirect function, treats what the value of the indirect function will treat that as a, the value of the indirect function is an address of a function, and whatever that returns is patched. So we need to find something that returns 0, so we can actually write 0 to end and stop all processing of relocation entries. And there's this nifty trick that ifunc is only treated as an indirect function if that random shindex thing, if that's not 0, and that's just another field in the symbol itself. So if we can set that, if we can have control over this this field right there, we can force this conditional branching. And I'll show exactly how that works. But first thing you need to do is just move the value you want to test to the location of this shindex. And then finally, this is what things will start looking like. You have this indirect function, you just copied some value to this index, and it doesn't really matter what at the moment. I'm just laying this out. And let's imagine that this value of this symbol points to something just returns 0. So that's at the address I listed, F0020. And then the relocation entry itself, offset, will point to wherever end is on the stack. And we can set this up during runtime. And so, return 0. So let's suppose shindex is 0. How does this entire thing pull together? Well, we use a relocation of type 64. We get the correct offset. So we copied some value to test, and that's 0. And again, we look, and we realize shindex is 0, So ifunc is not treated as an ifunc, and it just copies the value of the ifunc over. And it turns out that you can find something that will return 0 that is at a higher address than the relocation entries. So we will not break out of this loop. We'll keep on processing. And you can just fix up the value of end after all this happens as your next step if processing continues. And now if shindex is 1, we end up treating this function that it calls as the indirect function is actually treated as such. So suddenly 0 is returned and written out into the location specified by the relocation entry. And so this is how we get the conditional branching. Suddenly 0 is less than the next relocation entry, so we must stop. And once you stop, you have to end up wiring things that the address in which you set the dynamic table to will fix things up again before it continues processing. So there is lots of components of this branch that I'm not going to go into detail to, but there is code available. But before that, there's some other nifty tricks we can do. Not just beyond just having Turing complete computation, arbitrary computation out of just relocation entries. Some interesting things to do with it without the Turing completeness actually is we can just look up libraries at runtime. So if we remember this link map structure, and remember the beginning of the talk, the address of this structure is stored in the GOT. And the address of the GOT is stored in the dynamic table. So from the very start, you know where to look up this link map structure that points to, that you can access the address of every single library from, since these structures contain the base addresses of everything. So we need 4 instructions. So this is sort of an example of how we do it. So suppose you want to get, the second library in this link map structure has something. You want to be able to locate that. So it's located at this link map in the GOT. You follow the pointer to the next one, and ladder is the base adder. And you only need 4 instructions to do this, and 1 symbol. And the symbol, you initialize the symbol so that before it's ever loaded, the value of the symbol points to the second entry of the GOT. And to just run through this, we have the symbol, I'm going to call GOT, and that the value of that is just the address of where in memory you can find the link map structure. So first you do this move, which really is a mem copy, and you pull out the address of the link map structure and store it in the symbol. And now the next instruction does an add, and the address you want to add to is already in the symbol, so you want to actually look up the next field in this link map structure. And it turns out that's at offset hex 18. And so after the addition is done, you get the address of the link map, the next link map. And then you dereference again, or sorry, you dereference again, and you end up getting the beginning of the next link map structure. And from there, it turns out that the base address is stored at the beginning of the structure. So you do one final dereference, and suddenly the symbol you have contains the value of the base of whatever library you're looking for. And because the value in the symbol is now some interesting address, you can start using other instructions to add the address in your symbol to say some offset of a function that you're interested in. And so, just to step back for a moment and see what's really going on, just a high-level look of this is we have some executable we want to insert metadata into, and some idea of metadata we want, and perhaps a configuration. But the heresy toolkit is what we use to inject the metadata. And then we end up with some executable with crafted metadata. And then the runtime loader ends up processing the metadata and invoking this weird machine that we just inserted. So this configuration we need is actually something that can be just pulled out during compile time. The address of the GOT is fixed from, and you can look that up just from the executable. The address of a gadget that returns 0, you can just read through the file and through the code and find something that does that, or the machine code. And then the location and value of some of the dynamic table entries can be found at compile time, I'm calling. And the data collected by instructions at runtime is the base address of the loader and others. And so at the very beginning, you'll have a set of relocation entries that can hop through everything and find where the loader is, so that you can start locating link maps. Well, so you can start locating anything you're interested in the loader. And you actually need a loader to figure out where the stack is, because there's a static variable in there that points to something on the stack. And so I'm going to do a little demo. So using this hopping that we did to look at the link maps, I'm going to get ping to run as root. And it already runs setuid. And we used the Ubuntu's inetutils version 1.8. It just happens to be the code I pulled down. And it has some weird use scenario where you can specify in the command line -t in a string, and it's some type. And in the code itself, it does some string some string case comparison between the string and some string that is static, but the first parameter is something that you specify directly on the command line. So the idea is to, instead of having it call stir case comp, have it call exec, and suddenly you have control. You can specify on the command line some file for it to just start loading and running. The second thing you need to do, so you write relocation entries that find where libc is, and from there you can add the known offset to exec from the base of the library. You can overwrite the GOT entry for stir case comp with the address to the exec that you looked up during runtime. And then you want to overwrite setuid's entry with something that just returns. So we can have it not, it runs as root and then drops later to continue the rest of the execution. We want it to not drop out of root privileges. And setuid is how how it gets rid of is root permissions and just executes as a normal user. So we want to overwrite that in GOT with something that doesn't cause the privileges to be dropped. So, and just to show, this is the green is the metadata we added. There's like maybe 8 entries, and that does everything we need. And also a single symbol, which points to the GOT. So since the demo effect always bites me, and probably will, I have this pre-recorded. So ping backdoor, this utility, is what I wrote up that will create the relocations you need and insert them into the executable. And you also need to tell it where libc is so we can find exec. So we can see here, it's just locating everything we need, the address the offset of exec and the GOT entries we need is all figured out right then at compile time. And so here is what ping looks like, the usage. And there is this -t thing that we're going to be using. And so the next step is I'm just going to show you that we need to set ping as, we need to make set owned by root and add this setuid bit, because that ping actually needs to be root to operate. Yes. Yeah. Yeah, it was bigger. Full screen. It doesn't want to stretch. Lovely. Yeah. It's a video. Sorry. Oh, Zoom. Is there a Zoom on here? Video. Zoom. Thank you. Sorry. Bigger room than when I last showed the video. This will be interesting. So you're not going to be able to see everything. But without, so this is the, this backdoor is only invoked when the -t and some files given to it, something to execute, because that's how we overwrote this this string comparison thing, and that's only done when -t is specified. So if you, so I showed that if you can run it, and without this -t, it just runs, and you don't notice anything. But backdoor.sh just calls is just a bash file that opens a shell. That's all it does, and that's because exec will pass it weird arguments since we're doing something strange. But we just call exec with this shell, and since we're overwriting the string comparison, and I'm demo gods. Nope. What just happened?
Reduce the font size.
Reduce the, oh yes. So actually, yes, I need to reduce the font size in this case. So I actually opened up Ping in 2 different windows, and one of them is the original, and the other one is with the backdoor. Wait, where's my shell? Oh, somehow we skipped over that in the video. Yay, demo effect! So if you run ping with the backdoor, with this weird thing, you suddenly get this shell before you exit. There goes the wonderfulness. So the rest of this video, which I'm not going to show actually, because you won't be able to see it anyway, but it shows that the code is not changed, only the metadata. That's it. So but if you hash the two, you'll get different hashes, because they're different files. But it's only the metadata that's different, not the code. And that's the cool part about playing with metadata. Whoops. So read the fucking code. There is on GitHub a repository that contains a brainfuck to ELF compiler. So you give, if you're familiar with the language brainfuck, it will compile that down to ELF entries that, execute your brainfuck during load time. And there's also ping backdoor utility there, so you can take a look. And so now I want to move into Mako. There's some cool things over here, and if you're not familiar with Mako, it's the executable and linking format for OS X and iOS. So if we can do something interesting with that, let's go for it. And so I built a proof of concept exploit. It's very simple because it's preliminary work, but I think it's very much worth showing because I don't see much out there currently about Mako other than some very high-level things. So it's very similar to ELF on how it processes things to an extent. The metadata is structured very differently. Well, the metadata is structured very differently. And it also differs about how it processes relocation, when it does. And maybe it seems like it might be a little more powerful. We'll see. But again, we already have Turing complete, arbitrary computation with ELF. But I think there's some really interesting things that we might be able to do with Mako, and I've done some. So the relocation entries of Mako come compressed. I don't really think it's much shorter than these fixed size entries that we have, but so it goes. And similar to ELF, there's code that gets mapped, there's data that gets mapped, and so forth. So these are in different segments. There's one that's mapped at runtime that has no permissions. Text is the code. It gets mapped read, execute. Data gets mapped read, write, and link edit, which has all these relocation entries and symbol information gets mapped read only. However, you can change that just with a simple change in the metadata itself, because the metadata specifies how to load this segment. And so here's an example of relocation bytecode. And this is from Mako viewer, is what I'm using to view this. And there's not too much that parses it to this extent. But so these are a bunch of opcodes. And there will be a pointer to where you should start processing these opcodes during relocation time. And also they call relocation binding most of the time. And there's lazy binding and binding that's done during load time. But this is what some of the bytecode looks like. You'll have an instruction that says, well, so the relocator, the binder, keeps the metadata around, You set it up, and then it will, based on this data, it will make the relocation. So this metadata I'm talking about is, say, the segment that you want to bind, the offset, the symbol name, all the information you need to do a relocation is sort of set up by these opcodes, and then you say do bind, and the computation is performed. So here's an example. You set the segment as 2 and the offset as 64, so that means in the segments I read, like the data segments we're patching at offsets, 64. And then what library to look up the symbol, and flags and a name. So here it's specifying to look up exit in dilib. And then you say bind and done. And that's what the relocation entries look like. And you'll find different relocation entries for different purposes. There's a type that actually have different sort of instructions for rebase, and it's only processed if the libraries or executables loaded at some other base address. There's binding info, which is processed at load time. There's lazy binding info at linking, and export info, which I haven't really looked at yet. So there are no tools to actually add instructions. I've been doing all this by hand and testing it, and it works. And so if I want to, I just want to first go through the steps that we would take to edit this metadata, to inject or change it, really. So optionally, you can copy some instructions, some binding opcodes to some space at the end of the file, and then update some pointers to tell what. So LD dyne info, it's some structure. You can update its pointers to know where the new binding info is and the size of it. And then you need to update the size of the link edit segment so it maps everything to memory. And optionally, you can tell it to map the link edit segment to read-write, so we can start rewriting our own instructions. I've done this all by hand, although you can do a lot with a single byte change, which was kind of fun to play with. So if we go back to programs that use setuid and run as at an elevated privilege, and then try to drop it later on, I think that's an interesting place to focus. So overall, it's perform privilege operations, then call setuid, which drops the root privileges, and then usually execute everything else. So if we put on our thinking cap, so we want to craft metadata to prevent this call to setuid. So here's my simple setuid program. Again, this is all preliminary work, but all it does is it looks up its UID, prints it out, calls setuid to downgrade the privilege, and checks its UID again. And so you can't see the change, but you might be able to. It's a single byte. Before we'd made the change, there is instruction that, the binding instruction that specifies the string inline that it should be looking up the address of setuid during runtime linking. We changed that to get UID, and so this has an effect on runtime. The dynamic linker looks up the address of get UID instead of set UID, and get UID gets invoked instead. And so the root privileges remain. So we compiled it down, and set UID backdoor is the one with the 1 byte change. And to show you that it has 1 byte change, XXD is just a hex reader, and I just did a diff between the outputs of the hex reader, and it was so hard to find the 1 byte change that I highlighted in red. It's just I changed the S to a G, and suddenly, if you call the original, it downgrades its privilege, but if you call the one with this 1 byte difference, you remain as root afterwards. And I'd love to try this with something real, but this is preliminary work, and I'm still trying to build up the right tool set and so forth to do things that are a little more complex. And of course, if you have suggestions of debuggers for linkers, loaders in OS X or iOS or any methods, come see me. I'm definitely interested in hearing of what people think work. So some quick notes in PE. I want to look at it a little, but I think there's still some great examples of metadata weird machines there already. So if you're not familiar with Scape's locreate and published in Uninformed, it uses relocation entries as an unpacker. And that's pretty cool. So it patches code at runtime to unpack something. And I think that's pretty clever. And Korkami did some great stuff in PE. And so the PE101.korkami.com is a great resource if you want to look into PE. And he's done a pretty in-depth study on interesting effects that come from crafted metadata and crashing different loaders with metadata. And this cool PE PDF zip combo file example. So that's another great place to look. But for that, I'm going to end the talk, and I would really like to thank Sergey Bradis that has kind of inspired the work, and Sean Smith, who's my advisor. And there's some great folks that did work before me, the Greg Q, Eracy, Mayhem, Scape. There's a lot of good stuff to look at if you want to get into this sort of weird area of machines and executable in library and metadata. So for that, I will end for questions.
Thank you, Bex. So for questions, please line up at the microphones in the middle or in the left here from the stage. If you're leaving during the question and answering session, please respect it by leaving quietly. Thank you. First question from the middle.
Yeah, first of all, thank you for your talk. Great pictures as well. Definitely emphasizing on the weirdness.
Thank you.
I was wondering if there is any protection mechanism in the kernel that would inhibit messing with the metadata.
Well, it's kind of interesting you bring it up. We're looking, our lab is looking into something that will do that too. So really, one of the major issues is that anything mapped into memory space can access anything. Like code can access anything within a single process's memory space. And so we're exploiting that here. And also that the loader allows weird things to happen. Like normally I'd imagine a relocation entry shouldn't be patching itself, but it's allowed. But for the kernel side things, if we can start enforcing page level permissions, maybe this code cannot execute that. This is work that we have done in our lab and presented before, and it's called, what do we call it? ELFPAC. And so you can look into that, and there's some other work I'm sure that's going on that I can't remember off the top of my head. But yeah, definitely kernel changes would help.
All right, thank you.
Thank you.
And from the left.
Yes, I see weird machines as a social problem because whenever I try to convince people that it's not a good idea to build some, they do. Referring to philosophy of language as academic bullshit or something. I don't know. I think there's a fundamental principle at work that if you like having a more powerful language enables you to easier express yourself. How do you think one can motivate people who probably aren't really able to understand the implications of weird machines to not build something that enables us to build weird machines?
Well, one of the things we're trying to tackle we call the langsec problem.
Yeah, that's...
languages should not be more powerful than they need to be. And ideally, recognizers of languages, right? And ideally, they should only need perhaps just a regular expression. And there's just so many examples of showing that when you can't have if you can't tell that two recognizers or two data things that validate data, if you can't know that the two pieces of code do the same exact thing, you can let you have exploits. And there is some great work with Marathon Patterman and Len Sussman, Sergey Bradis. I think that's a good place to start looking. There's a good paper published by them in, I think, some security, IEEE security processing? No. Well, anyway.
But there's no down-to-earth...
Sorry?
There is no down-to-earth argument to stop doing such things that enable weird machines.
Right, and I think you just need to start just building up an arsenal of examples where there's an issue because there's a weird machine.
Thank you. Do we have questions from IRC? No questions from IRC. Middle again.
Hi, Rebecca. Thank you very much for your talk. It's very fascinating.
Thanks.
I was wondering if there's any directives inside of the the ELF metadata that can enable you to reload or overwrite something outside of the metadata, like maybe something in the text section or something like that.
Anything that's writable, yes.
Excellent.
Absolutely.
Awesome.
Thank you. From the left again.
Hi, is there a simple way from the linked list of shared objects to list all the shared objects loaded in all running processes at once without doing something like iterating over the procs file system, proc speed maps?
Well, this particular linked list exists in the process's memory, so it doesn't necessarily have the ability to traverse other processes in memory that are loaded. So
you basically always have to iterate over all the processes and their maps and their...
Yeah.
Okay.
Thank you. From the middle again.
How well does this play together with protection mechanisms like address space, layout randomization, or stack canaries to protect LDSO itself?
So I've shown that we can locate, as long as there's some way of locating this link map structure, which if the executable itself is not randomized, it doesn't matter that we can locate all the libraries. So I was showing the ping example, ASLR was enabled. It was just ping itself was mapped, to the same location. So it was not, what's it called? PIC code. Blanking on what that stands for, but unless the executable itself is not randomized, and even if it is, I don't have a reason to believe that this won't work. I just haven't looked into that yet. So, I mean, the metadata needs to be able to locate something. It needs to be able to locate itself. It needs to know where to patch. So, as long as you start crawling those substructures, you at least have data information over that. And especially within a single process, everything is mapped relative to each other. So. The code, you're not going to have like randomization of like space within. Well, I haven't seen it yet, and maybe it will be done in the future. But the text segment within a single object is always like within the same space of a data segment, and so you will always have that until someone starts patching segments and randomizing those. But you still, when you relocate, you need to know where everything is, at least for that particular executable. Or you need to be able to locate the other libraries which to patch. Otherwise, you're not going to be able to link.
Thank you. IRC? You need the mic, right? Here you go.
All right. Thank you very much. There are actually two questions from the IRC. First question would be whether it is sufficient to use linker and loader to fix this problem, or would you need to actually go and fix it in the kernel?
Well, maybe, but it would help if a linker and loader did more sanity checking. That would definitely decrease things. But in the end, it still needs to patch things that address, food. Like in the end, it needs to be able to do its job. So in just being able to patch things that you need, I don't see how I can really. I think it's a very hard problem. So when you look at my example using Mach-O, I changed a character, and suddenly so it's more than just the linker and loader. I think there's a couple of components that go in, and it seems like there needs to just be. I think all we'll be able to do is make it harder in the end, anyway, because there's always. You might be able to find very complex, weird machines that uses everything that, the absolute minimum that's necessary to complete what needs to be done. So.
Thank you very much. The other question that had popped up on the IRC is regarding your early comment about whether signatures are being applied to the code or to the entire executable itself. Mm-hmm. Could you elaborate a little bit more?
Would I elaborate more? I was looking through the ELF signed code to try to see. I've been told that doesn't sign metadata, and I wanted to actually show that in one of my slides, but I couldn't find it again. So I wouldn't want to really elaborate on that too much without being able to check myself fully. But it was more feedback that I've gotten from different developers. Oh crap, we don't sign the metadata in our executable. And I'm not sure if I would pass that on at this point.
Thank you. From the middle.
Actually, I couldn't follow most of the talk because it was too complex for me, so it's maybe a stupid question. Regarding the example with the ping utility, did I understand correctly that if you change the metadata, you have to change the binary, and you can't change it without being root?
Yeah, so for the ping,
so
yeah.
What is the goal of changing the metadata if I can change the binary itself?
Well, it's more of a backdoor, and that's what I was showing it as it is. So maybe you have root at one time, and you want to be able to access it in the future. So it's just starting to like build these components to escalate your privilege, and it's not gonna. If you don't have root to begin with, you're not going to be able to do anything there. But it's just sort of this interesting trick to insert a backdoor.
Thank you. Last question.
Hi. I was wondering how portable this is. I suppose it depends very much on the exact library linker version, so
yeah.
Probably different libc versions.
Yeah, and I haven't been spending too much time seeing how, the array. I haven't looked at the array of libc versions, and it'd be interesting to see how they change between each other, and then that's work that can be done. And I'm more interested in looking just at different executable formats to see more high-level issues.
Thanks.
Thank you so much. Give a round of applause for Bex.